Tenga qualcosa,
Mi sa che bisogna cambiare la soluzione. Okay, welcome to the October meetup of Data Science Milan. Today we're going to talk about 3D point cloud analysis using deep learning. I would like to give you a very quick introduction. I see there are a lot of loyal members we see almost every month and a few new faces, so I'll just give a brief introduction. Data Science Milan was born on February 2016. Nowadays it's more than 1,000 members, I think 1,200, something like that. And what we do is we organize events like this one, and we meet once a month roughly. The staff is composed by 9 people at the moment. We are divided into different roles. You'll find probably half of them, you'll find them here tonight. And those are actually the people that organize everything that happens behind the Science Milan. If you go on our website, we post everything there, every news, every announcement, every about new events. For example, next one is going to be in Tenaris. It's going to be on the 21st of November, and it's about computer vision in manufacturing. We also have a monthly digest. It's a newsletter. We only spam you once a month, and you can also send us your contents, and we can publish it. If you have not joined yet, you can do that on the website, datasciencemilan.org. Wallboard, again, if you have any message you'd like to post, send it to us, then we can spread the word for you. One is the social network, which is the Machine Intelligence Hub. You will find it on www.machineintelligencehub.com. You can use it on your website or from your laptop or from a mobile phone. And you will find also the Data Science Milan group, even if we're moving everything to the global network. So you find most of the members of the community, you can chat with them, you can ask questions, post contents, and so on. This is the company I work for. Do a little bit of promotion. It's a company doing social algorithms for human decision making. And at the moment we're hiring for data engineer, machine learning engineer, and natural language processing specialist positions. If you're interested to know more, then you can speak with me, you can send me a message after the event next day. So again, remember the community is open to everybody, so please take advantage of it. If you would like to spread the word, publish any content, please send it to us. Sponsors. Everything we organize is, we can do that thanks to our host and our sponsors. So first of all, let's thank our host, Bildo.
We are Bildo, we are a software company. This is Bildo. Those guys over there, and me also. One of the last guys is this one. And we are also hiring. So if you know somebody that wants to change work or, I don't know, find the first work, give us a call. If you want, there are some stickers on that and stuff.
Thank you.
Thank you.
So thank you, Bildo. And then I would like to thank Oliver James, which is our premium sponsor. You can find Mara over there. So Oliver James specializes in recruiting for data science and data engineering or data science related work, jobs. In particular, at the moment we have the following openings. The first one is a data scientist and machine learning expert role in a company based in Georgia and Florence, but the position is in Florence. There is a senior data scientist position in a telco company here in Milan, a lead data scientist position in an insurance, and a big data engineer position, again for an insurance company. If you want to know more, speak with Mara, or if you have any friend that is be interested, then you can introduce Mara. Our second sponsor is GitHub. I guess all of you already use GitHub, right? Raise your hand. If you use GitHub, raise your hand. Okay. Yeah, so GitHub is investing a lot in, it's been always the primary repository for development, software development, and now they're investing a lot to tailor their platform, their services specifically for data science, machine learning, AI projects. Okay, this is the agenda for today. Now we're gonna have the talk. Just gonna be just one talk, I guess, straight. Okay, and then I guess we would like to leave the venue before 9:30 because those guys probably want to go home as well. Okay, before we start the event, I need to ask you if you could support us on our social channels. We have an account on Twitter, Facebook, YouTube. Currently we are live on YouTube. We have our own LinkedIn page. So please support us by tweeting, posting pictures, spreading the word. Thank you very much and enjoy.
Good evening, everyone. My name is SK, and I will be speaking in English. Unfortunately, I'll not be able to speak in Italian or any other language, so please bear with me. I'm going to talk about point clouds today. And before I even talk about the technical topic, I just want to tell you, I saw the ad for the job NLP position. That reminds me of an interesting event that happened, I think, a year ago. Georgia Tech University, just a year ago, they developed an NLP model that can understand the language of a chicken. Georgia Tech developed an NLP model which can understand what a chicken is talking about. And do you know chicken actually have 50 to 70 words vocab? Human beings have a lot of big vocab, but I think chickens have 50 to 70 words vocabulary. Long time ago, before I spoke in a classroom, I was a little bit of curious to see how do I know what people are thinking when I'm talking about a topic. And the expert speaker said, you got to watch the body language and the facial expressions of the people. And he said, if people are smiling at you, that means they're listening to what you're talking about, they understand what you're talking. If they just don't even respond, they can't even, you can't see any smiles on their face, then they're not really getting what your point is. So please keep smiling once in a while to me, whenever I say something interesting, or even not interesting too, and I'll get more motivation to give information. I'm going to talk about point clouds. I'm going to talk about deep learning part of point clouds. I'll try to explain what's happening in the world, in the point cloud world. I'll be speaking for the next 45 minutes, and of course you can always interrupt me if you have any questions. Total, I think, not more than an hour I'll be speaking about. There's lots of information per slide. When I first started speaking in my life, people told me don't put too much of information in one single slide. I forgot that feedback in today's presentation. No, I'm just joking. I do have lots of information per slide, so if you want to take a picture of each slide, you're welcome to. Many times the information I have in that slide, if it's from a public source, I have the link at the bottom of the slide, so you can actually go back and read that paper or any other information regarding point cloud. Image processing is really becoming an extremely important activity in the world. 2012 was when the first CNNs or paper based on CNNs were introduced. 2015, the accuracy rates of CNNs went up tremendously. The 2D image processing I'm talking about. The top 5 error rate of a CNN-based model came down to 3.6%. In other words, every 100 images a model sees, it only makes mistakes in around 4 images. Do you know what the human error rate is for images? 5 to 6%. In other words, in 2015, CNNs have crossed human error rate in processing images. This is, of course, 2D images. But the number of sensors are going up. For example, LiDARs are increasing in number. They were extremely expensive, maybe I think 4 or 5 years ago. The prices are falling down. In the context of augmented reality, virtual reality, autonomous cars, even a medical field, the possibility of availability of 3D images is going up tremendously. You will find a lot more richer information in a 3D image, and hence the need to develop an AI model that can actually understand what's happening in the 3D image. Similar to the 2D image classifications, where the initial models were more focusing on classification examples, 3D image processing models, especially in point clouds, are focusing on trying to do a classification, but of late, in the last 6 months to 12 months, more papers have been published on understanding maybe the scene, or semantic segmentation, or even instant segmentations, or localizing and detection of images. And of course, the scene flow, like if you actually have a 2D video, and if you want to find out the flow of action, that is also being worked on in 3D image processing. The scene flow is also going to be being analyzed. I'm going to show a few papers. I will not be able to talk about what exactly we are doing in my company in terms of 3D image processing, but I will talk about some of the models that have really made a tremendous impact in the last year and a half. Similar to the 2D image processing, which really became popular from 2012 to 2015 to 16 and 17 even. By the way, the 2015 CNN image processing top 5 error rate came down to 3.6. 2016 it came down to 3%, and 2017 it came down to 2.6%. So the accuracy rates of these models are tremendously going up. Same is the case with 3D image processing, especially point clouds. There are other types of 3D images, and I'll talk a little bit about that, not too much about that. The research about point clouds is more recent phenomena. 2016, I have seen a few papers being published, but 2017 and 2018 is the time when a lot more papers are being published on 3D point clouds and deep learning probabilities and 3D point clouds. There are a variety of 3D information, 3D images you can capture, and 3D representations. You actually have Euclidean data structures and non-Euclidean data structures. Euclidean being you actually have a very systematic way of capturing, especially the distance metric of points. You have descriptors, you have projections. You actually can project a 3D image into a 2D space and then process that image to understand what's happening. You also have another type of data structure called RGBD, the 3 colors, red, green, blue, and D being the depth. You can capture the information. This is called so-called 2.5 dimension information. The RGB is in 2 dimension, and the depth is the half dimension. There is another way of measuring 3D data or capturing 3D information. It's called volumetric. So you can imagine every object, for example this, even though you see it's empty inside, you can imagine this to be a completely filled volume, and then you can process, you can apply deep learning to process the object. Multi-view is another way of data representation. If you have, let's say, you have a LiDAR sitting in this room and take an image of this entire room. LiDAR takes, one of the advanced LiDARs we manufacture, it takes 2 minutes to take an entire image of this room, including the people, the glass panes, the objects, and the size of the image is as high as half a terabyte. And it takes only 2 minutes to take that image. To get the same perspective of a 3D image, you can also do something called multi-view. In other words, if you take 2D images of the same object or the same room from multiple view locations, you can actually stitch it back, and because point clouds are canonical, you can convert data sets from one structure to the other structure. So you actually can have multi-view of the same object. For example, in this case, you have a chair, and if you want to get a 3D point view, you can take a camera, go around the chair, and take multiple pictures. It's called multi-view pictures, and then you can stitch it together. There are software solutions available which can make it a 3D representation. all these representations are some sort of a Euclidean data system, but there are images, there are 3D images which are non-Euclidean. Point clouds, graphs, and meshes are predominantly non-Euclidean, but there is a discussion among the scientists. You know, scientists, they're so intelligent, they'll never agree with each other. So there is a discussion on whether point clouds are really Euclidean or non-Euclidean. I would go with being Euclidean, but some people believe it's non-Euclidean. Many of the 3D image processing solutions in deep learning being proposed are on the Euclidean data set, and not really, it's not that easy to actually capture the non-Euclidean part. So if there is a non-Euclidean image, then you got to project it, you got to convert it into a Euclidean system. So for today's discussion, let's consider point clouds to be Euclidean data structures. Graphs and meshes, for example, mesh is a series of polygons, many times triangles, connected with each other, which show the representation of the image you're trying to capture. And then you can run a 3D, a deep learning model on it. Before I start explaining some of the solutions available in the current day world today, many times, many companies have use cases the following. One is semantic segmentation. For example, if you have an image of this room, where are the chairs, where are the people, where are the walls, where are the ceilings? This is typically the model that people want to figure out. So you can do a semantic segmentation. Or if you have just one single image, for example, if you take an image of a chair, you want the object to be identified, what class it belongs to. In 2016 and 2017, some of the research being published, companies or labs have been using the extension of the 2D image processing solutions into 3D images too. And I'm sure you've heard of CNNs. CNNs is one of the most common technique. I've seen even in 2015 and 2014, RNNs being used for image processing, but of late I think it's CNNs are the standard technique that's being used to process images. Some of the papers, initial papers in 2016 and 2017 have tried to use the same 2D CNNs, and sometimes there's something called a 3D image, 3D CNNs, but we'll talk about all of those things in a bit. This is a quick and a very high-level summary of what type of solutions you can apply, what type of solution approaches you can apply on the type of data you have. People don't use descriptors and projections anymore. If you use RGB data or volumetric data or multi-view data, you apply a variation of a CNN on all of these images to understand local level features and a global feature. For example, let me explain the local level feature and a global feature concept. Let's say you take an image of this room. The chairs have legs. If you want to process a point cloud very quickly, and if you don't give enough attention towards the local features of the chair, many times the model actually misses the legs or the back support, or many times the rods that appear in a chair, back of a chair. So the local features need to be also paid attention to, but then what happens? The computing cost is going to go up. But global features are, at a macro level, what type of objects can you see? For example, if it's a classification problem, the model can quickly converge and identify what class this object belongs to, whether it's a chair or a table or a person or a car or an animal or whatever information you want to capture. One of the first models that attracted my attention was in 2017, the published. It's called ONET, which is nothing else but OctNet. Octree or Octet or OctNet is a recursive data structure that divides a point clouds into 8 children, and it keeps on doing it. So you reach certain level when the entire point clouds are divided into nodes and subnodes and further subnodes, and each node have 8 subnodes, and again one of those subnodes will have 8 subnodes. You see, for example, if this is the image you want to do a classification of, you start breaking it down into 8 pieces, and keep on doing it until you feel you have enough local level features information, and then convert each of that ArcNet into a single feature space. And this is, after this, it's exactly the same how you do a 2D image processing. For example, if you have an image of a cat in a 2D, you have the RGB values, and if you run multiple kernels, you actually get multiple feature sets. The same concept is applied, but all that you do is break down the 3D image using arc-tree data structure. That was the earliest model. They got decent results, especially for classification, and the computing cost is not as expensive when it was done, when it was voxelized. Have you heard of the term voxelization? You see the term there, voxelized, you know what it is? Let me take an example of this cup again. If you have an object, you only see the external of it and assume that the entire object is filled with material of the same what you see outside. So you actually, it's a 3D volume object. It fills up the empty spaces and then creates one single 3D object, and the model starts assessing that voxelized image. It is easy to convert the 3D representation, in this case let's say point cloud, into voxelization, but the problem is the computing cost is going to be very high. The summary of this paper, if you want more information in the paper, I will put the link at the bottom of each slide. You can go back and check the paper. This is one of the earliest ones, did not become much popular. This paper too is exactly the same. They've used ArcNet. They made slightly different architecture. The architecture of the model is right there. It's a series of, once you convert the 3D image into a bunch of feature sets using ArcNets, they construct an architecture of multiple convolutions and then eventually do a fully connected network, and towards the end they'll do a softmax. The number of convolutions and the size of each convolutions and the max pooling is all shown there. But this paper and the previous paper both have the same concept of using ArcNets. 2017 PointNet is one of the pioneering paper. If you are interested in point clouds or using any type of 3D image processing, PointNet is one of the first models actually made a fantastic contribution towards identifying objects, classification of objects, and semantic segmentation. PointNet also, for the first time, used point clouds for the first time in the raw format. No pre-processing of point cloud was done when PointNet was invented. This, I think, students from a couple of students from Stanford published a paper in 2017. The primary objective in this, if you look into some of the comparisons of the model was already beating the state-of-the-art solutions in voxel-based, ArcNet-based, and other approaches till then. Let me explain how PointNet works. PointNet has to be invariant to transformation. Imagine you take a PointNet of this room. Whether you see it from here or see it from there, it's the same room. In other words, if you rotate the PointNet, it's still, all the objects in the room relative to each other remain the same. So it's invariant to rotation. So what the authors say, take the dimension of each point. Let's say you only take x, y, z dimensions. You can also add more dimensions if you want to. Let's say for ease of discussion, you just have x, y, z dimensions of each point. If you take the x, y, z of all the points, number of points being capital N, you can arrange them in a matrix, an array, and if you transform or rearrange any of those arrays, there won't be any difference in terms of what the point cloud is. So they take the raw inputs, put it through some type of a transformation. The exact details of the transformation you can read. It is nothing else but the skip net connections which are used in ResNet. It's almost the same, but you can read the information in the paper. But transforming those individual points using some the matrix multiplication and 3 by 3 transformations, and after that just using a simple multi-layer perceptron or an M. So take the single point, arrange them in an array, and give it to, put it first through some transformations as described here, and then put it through a bunch of multi-layer perceptrons. If once these data goes through multi-layer perceptron and towards the end they actually have a max pooling. Why do they use max pooling? They wanted to have a symmetric function on the point cloud, because point cloud is invariant to rotation. So what is a symmetric function? Symmetric function is that function when applied on a set of data in any order, in any sequence, the answer remains the same. For example, addition. 2 plus 3 and 3 plus 2 is the same. Multiplication. Pooling, max pooling, an average pooling, it's the same thing too. So they found the best value is when they apply max pooling on this transformed data, and the max pooling gives a single dimension vector which is a reflection of the global feature of the point cloud. In other words, if you have an image of a chair, now you have a single vector that represents that chair, that object, and then you can actually have scores of each class based on this single vector. So you have the global feature of the entire image, and then you can run a joint network which can understand additional information. For example, if you want to do classification each point, in other words called semantic segmentation, you could run another network. You have to concatenate the global feature with every point, and the model can understand which class these points belong to. In other words, semantic segmentation also becomes extremely easy. The reason this model became so popular is, as I mentioned earlier, this is the first time you can use raw point clouds as is without any transformation, and also they were beating state-of-the-art solutions till then based on ArcNets or voxelization or any other approaches, including 3D CNNs. The authors came out with another paper within 6 months called PointNet++. I think after this, but anyway, I want to talk about this approach. K-dimensional network, K-dimensional tree network, which is similar to ArcNet approach. You divide the point clouds into sub-nodes of 8 pieces and keep on doing it. K, I think, is 8 K-dimensional trees. You build K-dimensional trees and run a various model. They actually could beat PointNet and ArcNet too in their solution. Multi-view CNN is a model which came long before these models came out. I did not bring it up today. Multi-view CNN was also an impressive model, and this is nothing else but if you have a point cloud, convert that point cloud into multi-view 2D images, and then pack one on top of the other and run a regular CNNs on top. That model also ran really well for a while. For example, if you look into the class accuracy for the 40 class, this one says the data set is modeled at 40. The accuracy was very, very high. But the problem with multi-view CNN is to have so many images. How many images? Sometimes it's confusing too, depending upon the complexity of the image. Sometimes 8, sometimes 10, sometimes 15. Then comes the complication of computations. So 2017, again, sometime I think 6 months later after the first paper, these guys came out with the next model, PointNet++, where they found that the local level features were not being appropriately captured in the original PointNet model. In other words, as I mentioned earlier, if there are 4 chairs and a table right next to each other, sometimes the model will fail to pick the chair, the legs of the chair, which leg belongs to which chair, because it actually gets a little complicated. So the difference between PointNet++ and PointNet is the authors recommend that you run a PointNet model recursively on all the local features possible. So you pick a few points, whichever points you want to focus on, pick those points and run a PointNet on just only that and get the global feature vector out of it. And if you keep on doing it, the model actually is paying attention to the leg of each chair, let's say, the corner of each table, maybe the window in all around the walls. Every such information is being captured in PointNet++. I know, I think you have to move the camera all the time. Sorry for that, and I just can't. When I was a kid, I ate some spring, so I can't stand in one place. Yeah. That was a joke, by the way. Yeah. PointNet and PointNet++, both models together, have made tremendous impact on 3D image processing. For example, the accuracy rates of PointNet++ went up, even though the computation cost went up too, because now we are running multiple times PointNet model on the same image and then trying to identify. So this model not only does the classification, but also does very effectively semantic segmentation. In the PointNet model, some of the, even though it actually picks up and does a decent job, it was not effectively picking up, let's say, in the semantic segmentation, if you see the chair here, there's another chair there, the red and the black, but it was not actually capturing the legs of the chair or even legs of the table, or sometimes even the shade. The shade on the floor, because of the light of the roof and formed because of the table, that also was getting confusing. But PointNet++, the model actually could solve many of those problems. I think PointNet model, they have open sourced the code, I guess, I'm not very sure, but lots of pre-trained models of PointNet are available, just in case if you want to use for semantic segmentation. Still have any questions? There are only 2 reasons why you don't have any questions. First reason is I was so brilliant, I don't have any question. The other reason can be, oh my god, I just didn't make any sense at all till now. But I'll take somewhere between the two, not one of the two.
I have a question.
Yes.
Go ahead. I noticed if you go back to the PointNet model, like there is like an initial matrix multiplication for like, I guess it's for rotation of the PointNet. Is it similar to the approach they used in CapsuleNet at the beginning and in post-estimation? Can you highlight like the differences and like?
This is not the same as capsule network. No, it's not the same. That's a different topic entirely about capsule comparison. I can talk about offline, but Capsule, when they published, I think in October 2017, came out really with very, very high expectations. I've not seen enough papers being published on capsule network, so I'm not very sure that's really picking up. I know the difference between non-capsule network 2D image processing versus capsule network, because capsule actually captures the hierarchy of images. One of the famous examples I think Jeff Hinton talked about in capsule network was, if you show an image of a face with 2 eyes and a nose and a lips and ears, the model can predict it's a human face. But even if you move the one eye from here to here, move the lips from here to here and ears here, still the model thinks that's a human face. even though it's not anymore a human face, it's just some random thing. But the model has found all the individual components, whereas capsule networks actually captures the hierarchy of it. I don't think they're focusing on the hierarchy part of it at this point of time, because that's a very reason why they invented PointNet++, because here some of the local features were not being captured. That is different from capsule network, where capsule network identifies individual components, but especially pays attention towards hierarchy of those features. That's, in my opinion, was the fundamental contribution of Jeff Hinton when he announced capsule network. So I don't think that would even come in this context. Yeah, thank you for the question. I appreciate it. I found a very interesting paper again, published just I think 6 months ago, 1802. If you see the numbering scheme of archive, 1802 means sometime in Feb of this year the paper was published. Sparse lattice network. The entire point cloud was divided into sparse lattices. Something similar to the OCtNet and OCT data structure, but they use the word sparse lattices because they introduced a concept called bilateral convolutional layer. Let me explain that. Look at this image. So you have some points of point cloud randomly. If you draw a triangular mesh around these points, because originally point clouds are unordered, they don't have a sequence, they can randomly appear any way they want to, right? And the reason you could not use regular CNNs, because CNNs look for regular organized data. For example, in an image of a cat or a dog, which is a 2D image, you find every pixel is arranged in a certain order and every pixel has a value. But in point clouds, not every space has a point. So if you draw a splat in the space, and you'll see some random points. You see a point somewhere in the triangle here. Here you see a point at the vertex. This is another point right on the edge. And here you find somewhere deep inside, you find 2 points within a triangle. What you do is, to bring some order to these points, you allocate each point to the vertex using certain algorithm. For example, if this point is so close to this vertex, whatever is the value here, you will assign that value, more of that value to this vertex, less to these two vertices. So you are actually distributing the values of points to various vertices of this mesh. In this case, it's a triangle. It could be a square or any other polygon too. Once you distribute the points to various vertices, now the entire point cloud becomes a very organized structure. It is a series of triangles. It's a splat. It's a splat. And after that, you run a CNN model, which is no more a rectangular or a square shape. The kernel would be of the shape of the same splat you have used. For example, you see the small colored picture there. Do you have any laser pointer? No, it's okay. The shape of your kernel will be matching the shape of the splat, and you just slide to do the convolutions. And then the rest of the steps will be very similar to the 2D CNNs you do. Sparse lattice network, published in around 6-8 months ago, also accomplished tremendous results, especially in the semantic segmentation. If you look into semantic segmentations, the best part, the interesting part in this case is they actually not only came out with a model that can process the point cloud as is, it also can take point clouds and 2D images of the same scenario and run it together. So you actually have Splatnet which actually can take 3D images alone, 2D multi-view images alone, and then also do 2D multi-view images plus 3D point cloud, all combined into a single model, and then the model becoming a lot more accurate and precise for semantic segmentation and classification. A very wonderful, very nice model, but I don't know, we have a pre-trained model available, but if you guys are interested in any type of segmentation, if you're trying to look for today, I think it's easy. Now, why is semantic segmentation is a lot more important than just the classification part? If the real life examples, you don't have too many just classification examples alone, because when you take a point cloud image, it's always a complex image. You have multiple objects in it. So it just cannot be one single classification. Even localization and detection also does not work, because then you have so many occluded images too. Semantic segmentation works where you can identify the various objects and also draw the boundary line along those objects. So if you're using an autonomous car and the car is driving at the speed of 130 kilometers per hour in Italy, 120 in Zurich, 65 miles per hour in California, you want the model to be extremely quick and precise to identify where the road ends and where the tree starts and where the other car is. And you need to really have the semantic segmentation information available. Many of these models are sub-second response rates, but the response rates, even though is less, these models I think are not paying as much attention towards the response rate, but the accuracy rates are very, very high for Splatnet. MRTnet. What is the word MRT? I'll recollect the name of the reason for the MRT. In this model, for the first time, encoder-decoder concept was used. I've seen encoders and decoders being used predominantly in NLP, where you actually have an encoder which is trying to understand the input, let's say a sentence in certain language, and if you're doing a language translation, the decoder starts outputting the translated sentence in the other language, the target language and the source language. But for the first time, I've seen MRTnet using encoder and decoder, but otherwise the concept remaining the same. You take individual points, and sometimes they even reduce the density of the points too. For example, if an image is of certain density, you can drop it down by half or even further, and then the model can still perform better. Other than that, there's not much of a difference, but I see even they were better than these models, but the models are getting saturated now. You see 90%, 91.2%, 91.7%. The accuracy rates are inching up, not dramatically jumping compared to what used to be when PointNet came out. PointNet is already, I think people have already beaten PointNet, but not with a tremendous amount of accuracy rates. One additional good point of PointNet is if you drop the number of points by 50%, in other words, the density of your point cloud drops by 50%, PointNet as a model is so robust, the accuracy rates drop by only 2% or even less. So 50% of the points in your point cloud is eliminated. So imagine, and why would that be an interesting case? The interesting case is because if your LiDAR, the car is moving at such a fast speed, or things are moving, either the car moving or the objects are moving, the point clouds will not really capture all the information. So it's noisy point clouds. But even in that situation, the accuracy rates of PointNet is really, really high. That's another additional good feature of PointNet, which I think has not been beaten, even though overall the accuracy rates of other models are improving too. I have a couple of other models which also do a good job in classification and semantic segmentation, but these are based on their 2D counterpart. For example, there's a very famous model called SqueezeNet, which is a 2D classification and semantic segmentation model, and they've used the same approach and named it a squeeze seg, which is nothing else but two predominantly important points. One is you have the skip level connections. You actually have every layer, even though you're processing the information through a bunch of other convolutional layers, you still give the benefit of doubt by transferring the information to the other layer too. That's one point, the skip connections, and second is of course the convolutions and deconvolutions. You actually reduce the size of the feature set, and then you also do the deconvol to expand the shape or the size of the feature set. They have invented a term called file module, which is nothing else but you do a one by one kernel on the feature input, and then try to reduce the size of it, and you deconvolve in such a way and concatenate so that to bring the C dimension back to C and not C by 2 or C by 4. Otherwise, there's not much of a creativity in this model, except the fact that it's using C and ANDs, and the skip level connections and the deconvolutions. Point seg is a similar model too, as I mentioned earlier. There's a different model they picked up from 2D. Here, they again do the same convolutions and deconvolutions. Published very recently. One of the best part of this is if this is actually using the ModelNet dataset, which is more towards the objects you see on the streets, the accuracy rates are really high. I think the comparison of the models with squeeze seg, which I showed just a few seconds ago, versus this model point seg. There are other models called LMNet. I will not talk about it much. There's another model which really attracted our attention, came around 6 months ago. Here's an interesting one. You have 2D CNNs, so you actually have two-dimensional kernels which convolve on an image. And earlier 3D image processing, people started using 3D CNNs, which is nothing else but a 3D kernel. So in 2D kernels it used to be, let's say, 1 by 1 or 3 by 3. Now it's 1 by 1 by 1 or 3 by 3 by 3, and the cube-looking kernel is convolving on the image. Here the author said, if the point cloud is more of a spherical shape, and if you have information around you, because LiDAR captures information around you, it's almost like a spherical view, why not we have kernels which are also spherical in shape? That's the only differentiating factor in this. If you see, you have the entire image and you have a spherical convolutional kernel which actually convolves on the image. Spherical CNN was published. I think even though it shows good results, but I have not seen too many people using it. That's one differentiation. Fully convolutional point network is it's very similar. The interesting part is this model actually does an excellent job for indoor information. If you have offices, if you have a factory, which is in our case, I think it's a huge use case for us, trying to detect objects, especially if it's in an airport or an auditorium or a sports arena, you want to model to understand what's happening, like how many people are walking in, how many cars are walking, are being driven, so it can actually identify the indoor solutions. The network, I think, is again with the basic approach is very similar, again doing a bunch of convolutions, but they did a good job in terms of identifying various classes. If you are working on point clouds, there are lots and lots of data sets available. In 2012, when some of the companies have started using 2D image processing, there were not too many data sets, CFAR and ImageNet, and some of the very primary data sets available, but now there are a bunch of data sets available. These are all the data sets, for example, but ShapeNet and ModelNet, I think that's ModelNet. ShapeNet and ModelNet are the two predominantly used models. ModelNet actually has 40 class data structure. They also have a 10 class data set. If you want to work on any of these, but I'm not sure, some of the models, some of the data sets I didn't like. For example, Flying Things 3D is a synthetic data set. Sometimes it's not useful if you're trying to use the model for real life situations, but if you are into designing of components, you can use this data set to train your model on and then use it for further inference. I have some let me pick a different model. I have a couple of models here to show the flow of action. We as a company have solutions working for smart cities, and in smart cities you want to find out the action in a video. The regular video, you have the 2D video which is being fed in. If you have cameras on the streets and you want to find out the action, there are solutions available. Let's say there is a crime event happening right at that time. The model sitting on a surveillance camera can decipher what's happening and then alert the right authorities. Action flow in a point cloud image is a different ballgame. There are very early stage papers being published. FlowNet 3D is one. Right now, some of the autonomous car companies are using models similar to this to detect the action. It's not just classification or semantic segmentation, which can be done by taking a snapshot image, but action flow is sometimes interesting for example, if your autonomous car is going on the street and there's another car with a driver, a human driver sitting in the car, you want to look at what the driver is doing sometimes. It's not just watching the car alone, but sometimes looking at the driver to see, has the driver seen this car, and then taking appropriate actions like a human being. That's what you normally do. Even though there's a car coming, you only not just only see the car, but you also see where the driver is looking, just to make sure the person observed you or not. For that type of use cases, flow of action in a 3D point cloud image is important. These are a couple of papers here. I will not get into the details. This is the second one I found, and I'm sure you've heard of YOLO 2D. If those who have not heard of it, you only live once, is what YOLO stands for. They came out with a really good solution. The first YOLO version 1 I think was only 45 frames per second. YOLO 2 was 224 frames per second. Really extremely good response rate and high accuracy. And YOLO 3, I think the accuracy dropped, but the computation cost went down dramatically. They started putting YOLO 3 on a mobile device too. So YOLO 3D is a new model that actually starts applying almost the same logic of YOLO 2D onto the 3D images. It's not picked up the popularity yet, but these are the two models I've seen which are showing promise in detecting flow of action in 3D images. PointFlowNet is another model. It's a hugely complex architecture. I don't want to explain, but these are the three models available, just in case if you guys are working on trying to detect flow of action. What are the libraries that are available for you to find solutions for yourself? Point Cloud library is an open source library that's available, which you can use to create your own point cloud solutions. They also have a bunch of modules which will help you pre-process, process, develop an architecture, and then run the whole model as you want. There are a bunch of open source sponsors available. This is one library I found, and then Cilantro is another library I found if you are trying to develop solutions for point clouds. They have a good library. The library is growing, and if you want to just play with point clouds, it'll be a good place. And I mentioned to you the datasets available. You can download a dataset, use this libraries to develop your own solutions. That's it. Thank you. Thank you. I'll be happy if you have any questions. Yes.
Can you tell us some fields of application of the point map and similar algorithms? Because I saw that you mentioned a lot of models that are very recent and maybe not yet production ready, I think, but maybe PointNet is.
PointNet is, and also what I shared today are published papers. Google wouldn't publish how they're using the point cloud or 3D LiDAR information processing for their autonomous cars. Similarly, I think Tesla will not reveal, I guess. So I'm sure there are a bunch of other solutions too, including Baidu actually have their own autonomous car. The use cases are plenty. As I mentioned earlier, I think in CT scans, in healthcare industry, you want a lot more effective image processing using 3D images too. Right now, I think you're taking a snapshot of every slice of a 3D image and then making sense out of it. It doesn't make sense all the time. So in medical industry, also augmented reality. If you want the model to look at an augmented reality image and make sense out of it, that's another industry too, which is making tremendous. Any construction, building construction, factory construction, you are trying to understand what's happening in a factory, including robots which actually go inside a factory, have to have a 3D view of what's of how to make sense what's happening. Of course, the most important area which you use point clouds is autonomous cars. The LiDAR sitting on a car can figure out what's happening. And when I say autonomous car, it's just not autonomous car, autonomous vehicles, for example, a drone or a robot which is running around. We have a use case in our company where the customers want to find out if the door is open or not, because that's a security threat, and the robot, what it does is, it's going around everywhere and just looking at the doors and finding out if the door is open or not. But it's not that simple a case in a factory environment because the doors don't look the same. Sometimes you have, the doors are occluded, partially covered because workers may leave some objects in the way of the door or they're hanging clothes on the door. The doors can't be seen, the model has to be intelligent to figure out. But that is only a 2D image, but we are trying to use drones. We have drones which is going around, we have satellite images, and also we have indoors, let's say factories and building construction, where we have 3D images. So anytime, everywhere you have a 2D image processing requirement as of today, in a year or two from now, that 2D becomes 3D image. Because the sensor costs are going down, so there will be a lot more 3D images available, and hence models have to be a lot more intelligent. So it's the same scenario repeating 2012 to 2015, repeating 2018 to 2020 maybe. 2012 was one, CNN was introduced, and 2015 CNN crossed the human performance. 2017-18 is when you find models being introduced for point clouds. Maybe I think in a couple of years you'll find models really surpassing human capability and using 3D images.
And when it comes down to libraries, because for the CNS there are so many libraries, I mean, from TensorFlow to MXNet to CMPK, and for point clouds?
Those are the two libraries what I showed are what right now available, Point Cloud Library and Cilantro are the two libraries available. These are open source independently being developed by a community of people. I have not checked whether TensorFlow is adding anything on 3D based, but knowing Google, I'm sure they will add soon something to that too. But also remember, all the papers are published, which are really important ones, are published in 2017, 2018. So it's really research information which people are trying to develop solutions. TensorFlow really picks up once a paper is published. They do an API call, they do a library that works on that. So I'm sure it should be coming soon, but I don't know as of today they're available or not. But many companies are developing, like we are developing our own point cloud solutions too. Yeah, it's not part of those 3D libraries except this and point cloud library.
We had a brief discussion before the beginning of the talk about data collection. So
What collection, sorry?
Data collection.
Okay.
So you were talking about like different types of technologies available to do that. Can you give us just an overview of what's available now, the costs, and what's it's going to become like mainstream and cheap?
Yeah. LiDARs, I think, are one of the
quick specific question. When will I have like a 3D camera
Good question. I'll answer that question last, but before that, data collection and the cost, like LiDARs are the most commonly used point cloud sensors that's being used predominantly in autonomous cars or autonomous vehicle, but I think there are other instances too. We do have, in my company, we have a 3D image point cloud. It's called BLK360. We just announced, I think, in July in Las Vegas convention, and it's already in the market. That's the one I was talking about. It takes only 2 minutes to create a very intricate inside of a factory with lots and lots of pipes and lots of machinery. It really creates a very, very intelligent, high definition point cloud in less than 2 minutes. And many times the image size is around half a terabyte, and and we are also have in the roadmap, I think in a year or two from now, to come out with extremely small, compact point cloud LiDAR. But the costs are really coming down. As I remember, I think 4 or 5 years ago when Google cars used to run around in California. I don't know how many of you have driven cars. Many times when I drive, I see a Google car going by, and there's some Google engineer sitting and working on his computer and listening to music, not paying attention to the road, but the car is really driving on its own. And once in a while, if I want to really have fun with the car, I drive my car close to the car, and that slows down or change lanes or whatever. And it's thinking, oh, this guy is messing with me, but still, the car doesn't do anything. The cars have been running in California, autonomous cars. You can see even today if you drive around. When Google came out with this, when they made public this autonomous car, I remember I think LiDARs used to cost $20,000 US, but now I think it's tremendously dropping, maybe even $5,000 now. But there will be a day, I think, like you said, you can just buy a phone. Your phone will come with a LiDAR in it, and it actually can capture the pictures. Some of the AR, VR solutions which are already available as apps, let's say, I think IKEA app will help you do the AR and VR for your house. You select a chair online on IKEA, and then if you want to find out whether it fits into your room or not, it does the augmented reality. So that type of SDKs are already available in the phone. For example, Apple has released their SDK called what's the ML? There's a name they've given. I forgot the SDK. So the costs are coming down. More number of users are coming out. More solutions are available in terms of how you can process it and the time computations it takes. So maybe in a year from now, my opinion is, because like I know my company is announcing something, the next generation, which I'm sure definitely better than what we have today, which is already, I think it's just only 2 pounds. It weighs 2 pounds, and this looks this tall. You can hold it in your hand or put it in your backpack and then walk around in a factory and do it. And I'm sure maybe a lot more better versions will be coming out soon. So a year from now or 2 years from now, some of the phones will actually have the capability to have 3D image, 3D point cloud image too. Okay, thank you very much. Appreciate your time. Yeah.